right, the first one says, the extractor arms which vent toxic fumes are used to protect people in the lab from breathing in which of the following? Circle your answer. Well, in the case of aqueous sodium carbonate, you have an ionic compound dissolved in water. That's not going to be volatile. Volatile in chemistry means easily vaporized. So this is an ionic compound dissolved in water, so not easily vaporized. Sodium sulfate is an ionic solid with a very, very high boiling point, not easily vaporized, not volatile. That's not going to protect you. 10% sodium hydroxide solution is the same. It's an ionic compound dissolved in water. It's not very volatile. The one that is volatile is hydrogen bromide gas, because it's a gas at room temperature, so it goes into the gas phase readily, and the extractor arms are designed to prevent you from breathing in fumes, so the gaseous one is the one that you have to worry about. All right, so in question 2, we have an ester. Okay, this is a methyl benzoate. So this is benzoic acid with a methyl group on it. So methyl benzoate ester. So it asks us to find out how many hydrogens are in this molecule. So carbon has 4 bonds. So if we look at this carbon, what is shown is 1, 2, 3 bonds. So it must have a hydrogen. Same here, has 1, 2, 3 bonds. So it must have a hydrogen, and that's true here, here, and here as well. So the benzene ring, or the phenyl ring, has 5 hydrogens on it. If we look here, this carbon has 1, 2, 3, 4 bonds, so no other hydrogens. The oxygen doesn't have a hydrogen on it. And then here we have a carbon, which is having 3 hydrogens on it. This is called the methyl group, of course. So we have 3 here plus 5 here for a total of 8 hydrogens on this methyl benzoate. All right, so the next question asks us which carbocation is the most stable. So first of all, carbocation is a positively charged carbon, not a negatively charged carbon. Those are carbanions, so those are out. All right, so carbocations. In this case, we have a primary, a secondary, and a tertiary. So primary is because this carbon with the positive charge is bonded to one other carbon. So this is a primary carbocation. This carbon with the positive charge is bonded to 2 other carbons, so this is a secondary carbocation. And this carbon with the positive charge is bonded to 1, 2, 3 other carbons, so this is a tertiary carbocation. Tertiary carbocations are the most stable because these methyl groups can back donate a little bit of electron density, stabilizing the carbocation. So having 3 methyl groups is more stable than having 2 carbon containing groups or 1 carbon containing group, because you can get more back donation with 3 than you can with 2 or 1. So question 4 asks us which of the following answers best explains why the product shown below would be formed in the reaction, and then circle your answer. Okay, and then in question 5 we're asked to write the mechanism for the formation of the major organic product of the exact same reaction. So the first thing we need to realize is that the product is the product that's shown right there. So I'm going to kind of do these together because it's going to be easier to write which of the following best explains why if we see what the mechanism is. So in this case, what we have is we have this alkene reacting with HBr. So in this case, it asks us to specifically identify the nucleophile and the electrophile in the first step of the reaction. The pi bond acts as the nucleophile and attaches to the H like that, and the H plus acts as the electrophile. So the nucleophile is the pi bond and the H plus is the electrophile. Then you get Br minus, so these electrons just go on to Br and you end up with Br minus. Now the question is, does the H add to this side of the double bond or does it add to this side of the double bond? And the answer to that question is from Markovnikov's rule. So Markovnikov's rule tells us that the H, the new H, mind you, there are already 2 H's on here, but the new H, the one that I'm now showing here, will add to the less substituted side. And when we look at this, we now have here where this had these electrons around it and it no longer does. So this carbon was on a double bond, now it's not. Said another way, there's only 1 H on here, okay, and now you have a 3 bonded carbon. It's bonded to 2 other carbons and an H that I'm not showing. So this is positively charged. And we end up with a carbocation. The reason that the H by Markovnikov's rule goes to the less substituted side is because you're going to form the secondary carbocation, which is the more stable carbocation. This also answers question 4. It says which of the following answer best explains why the product shown below would be formed in the reaction. So the reason is a secondary carbocation is formed. If a primary carbocation was formed, the bromine would add over here. And then there is no carbanion, so these don't make any sense. Note that we still have this Br minus that we formed when this bond broke. So we have the Br minus here. The Br minus then acts as the nucleophile, and it attacks the carbocation, and what we end up with is the product like this. So Markovnikov's rule tells us that the H is going to add to the less substituted side, and the nucleophile is going to add to the more substituted side. That's not technically Markovnikov's rule. The H is for Markovnikov's rule. All right, but that's effectively what happens because we go through the secondary carbocation intermediate and not the primary carbocation intermediate, which is answering question 4. All right, so like before, we're going to kind of do 2 questions in a row here because 6 and 7 are very related to each other. It says, what is the first step of the mechanism for the reaction shown below? Circle your answer. And then it says, what is the electrophile in the first step of the mechanism for the reaction shown below? So in this case, what we have is we have a strong acid reacting with an alcohol, and we want to get an alkene and water. So effectively, what we're going to do here is we're going to go through an E1 type mechanism where we're going to protonate the alcohol to form water. Then water is going to leave. Then we're going to get a hydrogen here. That's going to get pulled off by some base. And we're going to basically end up with an alkene as shown here. All right, so getting back to the original question, what's going to happen here is we're going to have 2 lone pairs on this oxygen that are not shown, and they are going to grab that proton. So in the first step of the mechanism, what's going to happen is we're going to form water here, and then this water is going to leave, and then again a base is going to pull off the adjacent hydrogen to form the alkene in an elimination reaction. So the first step of the mechanism, a lone pair of electrons on the alcohol, oxygen, attacks a proton from the acid. So choice letter A, as shown here. Okay, because OH isn't a good leaving group, but water is. And then it says, what is the electrophile in the first step of the mechanism for the reaction shown below? So the lone pair on the oxygen of the alcohol acts as the nucleophile, and the H plus acts as the electrophile. So the proton from the sulfuric acid is the electrophile, because the nucleophile is looking for a positive charge and it finds H plus. The H plus, or the proton from the H2SO4, is going to act as the electrophile. All right, so last question says, the dehydration reaction shown below was completed and the product is characterized by gas chromatography GC. So this is the same reaction we were looking at before. We have cyclohexanol being dehydrated to form cyclohexene. Again, this comes in, grabs the H+, this forms water, that leaves, these H is pulled off by some base to reform, to form the alkene. It's an elimination reaction. It says, which of the compounds, cyclohexanol or cyclohexene, do you expect to have the higher boiling point? Well, the one with the higher boiling point is going to be your cyclohexanol. Why? This has an OH group up on it, which has hydrogen bonding. This molecule really only has dispersion forces. So we have a molecule that's polar and has hydrogen bonding, and we have one that only has dispersion forces. So since this has stronger intermolecular forces, it's going to be expected to have the higher boiling point. And as usual, I'm not going to write the explanation, I'm going to say the explanation. All right, it says, the chromatogram below is of a sample of cyclohexanol and cyclohexene, standards diluted in acetone. The acetone peak has been cut out for clarity. Label the cyclohexanol and the cyclohexene peaks below in the GC. Well, because of what we just talked about, cyclohexene is going to have a lower boiling point than cyclohexanol, because this acid which has the higher boiling point. we can reasonably expect that the cyclohexene is going to come out first in the GC, and what's going to come out second in the GC is the cyclohexanol. Higher boiling point is going to have a higher retention time. Lower boiling point, lower retention time. And this is a standard. So basically we just mix these two things together that we buy from the chemical companies, dissolve them in acetone, shoot them in the GC, and then we can see their retention times. And you'll see here this is somewhere around, I don't know, 2.2-ish minutes, okay? And this one's somewhere around 3.4 minutes. It says the chromatogram below is a student sample of the product of the reaction above completed using the same procedure used in this course. This sample was run using the GC instrument and the method in the standard sample above. The product is worked up so that any sulfuric acid is removed by acid-base extraction. But it is possible that some starting material remains in the sample. Identify the peaks in the chromatogram below. Comment on the purity of the sample. Is there any starting material present? So if we compare these two peaks, you'll notice that the retention times are the same. This one's somewhere around 3.4 minutes, somewhere around 2.2 minutes. So this one is still the cyclohexene. It doesn't matter if it's before the reaction, after the reaction, or the standard. The retention time for this mixture with a peak around 2.2 minutes is going to be your cyclohexene. This one is still your cyclohexanol. Again, it doesn't matter when, although it's unlikely to have any of this before the reaction, but it doesn't matter when you have this mixture. Now, it is important to note that retention times are not absolute, right? If you take some unknown mixture and shoot it in there, you can't just assume it has the same retention time as the same compound. That said, if the mixture is known, if you know what could be in it, then the retention time is telling. So in this case, we have some cyclohexanol here. There's certainly less of it than there was in the standard relative to the amount of cyclohexene, but that said, it is not perfectly pure. There is starting material present. Remember, our goal was to convert cyclohexanol to cyclohexene, and our product has some cyclohexanol in it, meaning that it's not perfectly pure. Thank you for watching this video. I hope you found it helpful.